Okay, let's work on lab number 3. So later on in this lab, we will meet for the first time the oscilloscope, and I'll go through the oscilloscope tutorial on video, and then I hope that makes it a little faster for you to go through the oscilloscope tutorial yourself in our first class meeting next Tuesday. Okay, return to or rebuild the 1K, 2K voltage divider you built in the previous lab. So I think that looked like we had the power supply here, and I don't know yet what voltage we're going to use for it. And I think we want the output to be 2/3, not 1/3 of the input. So we'll put the 1K resistor here, and we'll put the 2K resistor here, and we'll call this ground, and we'll call this our output, and we want this to be 9 volts. Okay, so I think this is what you want to build. 1K, 2K voltage divider, then we're going to attach a second voltage divider made with resistors that are 100 times as big. So this is the output of the first stage, but I guess now we'll add a second stage. So basically this first voltage divider is going to play the role of power supply for the second voltage divider. So here is 100K ohms, and then over here we have 200K ohms, and this is still ground. And I'm not sure what to call these points. I'm going to call this point on the circuit A, and I'll call this point on the circuit B. So if we had not connected, if we cover this thing up, then it doesn't exist. It's just an open circuit on the right hand side underneath my hand. Then the voltage at point A is 2/3 of 9 volts, which is 6 volts. Then if we had a perfect 6 volt power supply underneath my hand, so instead of being the output of a voltage divider, it is the DC power supply set for 6 volts, then the voltage at B would be 2/3 of 6 volts, which is 4 volts. Now, the question is, what are the actual voltages at A and B, given that we've taken one voltage divider and then we've wired up a second voltage divider to its output. So point A is the output of the first voltage divider, and point B is the output of the second voltage divider with respect to ground. Using our rule of thumb, we know that the input resistance of this second voltage divider, assuming there's nothing connected at B, assuming no current is being drawn at this output, so the input resistance of this downstream voltage divider is 300K. It's just 100 kilo ohms plus 200 kilo ohms. They're in series. So that means if you disconnect this and you measure the resistance between here and ground, if there's no current drawn at B, so either nothing is connected at B or something like a perfect voltmeter with extremely high input resistance is connected at B, then this resistance between these two nodes is just the series combination of 100K and 200K, so it's 300 kilo ohms. Meanwhile, we know that the Thevenin resistance of this upstream voltage divider is 667 ohms, 2/3 of a kilo ohm. So 300 kilo ohms is much, much bigger than 667 ohms. So if we say, yes, 300 kilo ohms is much, 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 much bigger than 667 ohms, we say, well, voltage A is 2/3 of 9 volts, and voltage, which is 6 volts, and voltage B is 2/3 of 6 volts, which is 4 volts. And you say, well, how different do we expect that to be in reality? So a Thevenin model for this upstream voltage divider looks like a 6 volt perfect voltage source in series with R Thevenin, which is 667 ohms. So that would be our Thevenin model for everything to the left of point A. And then we can replace everything to the right of point A with this series combination. So that would be, so what we're loading the upstream, the first voltage divider with, is something whose input resistance is 300 kilo ohms. So this is like 300 kilo ohms. So then the actual voltage at A should be 6 volts times 300 kilo ohms over 300.667 kilo ohms, which is 5.987 volts. That is so close to 6 volts that in order to know whether we're seeing 5.987 volts or 6.000 volts, we would probably have to use the actual measured component values of our resistors instead of just using the nominal value. This is about a 0.2% effect, and we're using 1% resistors. So in order to know whether or not we're seeing an effect so small, we would need to use our actual measured component value. Okay, now I probably got ahead of the text. Keep in mind the Thevenin equivalent circuit of the first divider, which is this. In the Thevenin equivalent circuit, R Thevenin is often referred to as the source resistance or the output resistance of the first divider. Yeah, Thevenin resistance, source resistance, output resistance, these are interchangeable terms. What is the input resistance of the second divider? It is 300 kilo ohms. What does the first divider see as the total resistance of its load, which is the second voltage divider? It sees these two things in series, 300 kilo ohms. What do you expect for V out 1 and V out 2? So I expect pretty darn close to 6 volts, so it turns out to be 5.987 volts. And then 2/3 of that, because this is a 2-to-1 voltage divider. So 2/3 of 5.987 volts, which will turn out to be 3.991 volts. So unless if we just follow our usual habit and use the nominal values of our components instead of the measured values, then we won't be able to tell the difference between 5.987 volts and 6 volts, and we won't be able to tell the difference between 3.99 volts and 4 volts. And I think that's okay, because we will see a larger effect on the next page. So let's wire this up and see what we see. It turns out that right at our bench over to the right, just out of view of the camera, we have little drawers that have 1K and 2K and 100K resistors readily available. But I had to go into the back room to find a 200K resistor. And actually the background color on this 1% resistor is much nicer than the background color on most of our other 1% resistors. I really like this brand better. So you can actually see very clearly red, black, black, orange, and then a big wide brown stripe. So the big wide brown stripe means this is a 1% resistor. So its actual value should be within 1% of its nominal value. 2003, because, okay, so black, brown, red, orange, yellow, green, and so on. So brown, red, orange. So orange is 3, red is 2. So this is red, black, black, orange, which is 2003. That means 200 times 10 to the 3, 200 kilo ohms. Now let's measure this 200K resistor with our ohm meter, which from the end of the previous lab we left in the current measuring configuration. So I'll pull this out of here and push it into here, the volt ohms input, and I'll put it in ohms mode. Then I'll measure my 200K resistor. Oh, now I see I have these. I really like having the two little wires on the spring clips, but to measure a resistor's resistance, I want to take them out. I get 199.5K. Okay, so that's a half part in 200, a quarter part in 100. So I guess that's about 0.25% tolerance. That's definitely within the 1% tolerance. Okay, so this is 200K within about 1/4%. I'll just stick this over here for the moment. Let's pick out a 100K resistor. I guess we expect that to be brown, black, black, orange, and then a brown stripe to indicate that it's a 1% tolerance resistor. This is the style that is hard to read, but I guess you can take my word for it. It says brown, black, black, orange, and then there's a brown stripe on the right. So I'll just put that over here. I won't do anything with it yet. And then let's find a 1K resistor. So that should be brown, black, black, brown, and then a brown stripe for 1%. This is pretty hard to see with the blue background. Okay, brown, black, black, brown, and then a space and a brown stripe for 1%. So that's our 1K resistor. We'll just put over here somewhere. And, oh, I should measure him too. So I'll measure the 1K resistor. I see 0.993K. Alright, so again, that seems to be, that's good to what, about 0.7%? I think we neglected to measure the 100K resistor, so let's measure that while we're here. it says 99.2 kilo ohms. Okay, so that's again good to less than 1%. And let's find the 2K resistor. So this is red, black, black, brown. The stripes really aren't that interesting. Red, black, black, brown, and then the brown 1% stripe. I'll measure that also, and I get 1.986 kilo ohms. I guess anything between 1.98 and 2 would be within 1% tolerance. So that seems to be within the 1% tolerance. Okay, I will try to make the physical circuit resemble my schematic diagram. Here is the positive power supply voltage coming in from the DC power supply. Here is the ground wire from the DC power supply. So I will use the 1K resistor to go from this positive supply voltage to this point. So this will be point A on my schematic. And then I'll take the 2K resistor. I was looking for that red stripe to confirm. Take the 2K resistor, and I'll go from node A down to ground, and then I'll take the 100K resistor. I'm just looking for the brown stripe to confirm, and that will go from node A to someplace on the right that I'll call node B, and then I'll take the 200K resistor, and I was looking for the red stripe again to confirm, and I'll go from node B down to ground. I could even go a little bit over to the right so that it looks even a little bit more like our schematic diagram. Okay, so you see, I think this really does resemble pretty well our schematic diagram. Here's the 1K resistor, here's the 2K resistor, here's the 100K resistor, here's the 200K resistor. So this little column is node A, and this little column is node B. And I'll take this voltmeter, and I'll put my little, I could just grab onto the leads of the resistors, but I kind of like using the little wires. So I'm going to grab ground there, and so I'll grab this little piece of red wire and put that at node A, and I'll slide this over to volts mode, and again the red cable is in the volt ohm input. Then I'll take the other voltmeter, and so its little red cable is in the volt ohm input. Put it on volts mode. Then I'll put its black lead into the ground row, and I'll put its red lead into node B, and then I'll turn on the Regal power supply. It takes a moment to warm up. Then we'll say 9 volts. Okay, so I'll type in 9 volts and I'll say on, and this says 9.00 volts. Okay, and over here at node A I get 5.976 volts, and over here at node B I get 3.971 volts. And again, simply taking the 1% tolerance on our components and not using the measured values, we really can't tell the difference here between this being exactly 6 and this being exactly 4 versus this being 0.2% smaller than the nominal value because of the loading effect of the second voltage divider on the first one. So I guess at the level of 1% precision, this is exactly 6 volts and this is exactly 4 volts, which is what we expect because the input resistance of the second voltage divider is orders of magnitude larger than the output resistance, also known as the Thevenin resistance, of the first voltage divider. So I basically predict, VA equals 6.0 volts, VB equals 4.0 volts to, like the 1% level. And I measure VA is 5.98 volts, VB is 3.97 volts. Now we want to replace the second voltage divider, the 100K, 200K divider, with instead a second 1K, 2K voltage divider. So we'll draw a schematic of that circuit. So here is my 9 volt power supply, and then this is 1 kilo ohm. Here's node A. This is 2 kilo ohms, and then this is ground. So now the second voltage divider has a 1 kilo ohm resistor here. Here's node B, and then we have 2 kilo ohm resistor here. So what we'll see in this case is that the voltages at A and B are in fact significantly different from the 6 volts and 4 volts that we measured on the previous page, because if I ask what is the Thevenin resistance of this first voltage divider, it is 667 ohms as it was before, but the input resistance of this second voltage divider now is 1K plus 2K is 3 kilo ohms. So the predicted VA, now you're going to have to bear with me if you're feeling really impatient that I'm not simply using Kirchhoff's rules and solving this circuit using the techniques that you learned in freshman physics. I feel your pain, but bear with me because we're trying to use this circuit that you know how to analyze using techniques you learned in the past. We're trying to use this circuit as a specific example to illustrate the general point that the presence of a downstream circuit fragment affects the voltage delivered by an upstream circuit fragment, and the degree to which the presence of this downstream circuit fragment affects the output voltage of this upstream circuit fragment depends on the ratio of the input resistance of the downstream circuit to the output resistance, also known as the Thevenin resistance, of the upstream circuit. So we predicted VA is 9 volts times 2 kilo ohms over 1 kilo ohm plus 2 kilo ohms. So this is what you would get with nothing plugged into the output of A. So this would be, so if I just cover up the downstream circuit and I say that what's underneath my hand is an open circuit, then this would be what you predict for A. And that's basically what we measured on the previous page. We got 2/3 of 9 volts was 6 volts. But now we're going to multiply this by a factor that I need to come up with a good noun phrase for, but I often call it the Thevenin factor or the loading factor. I haven't figured out what the official terminology is. But I'm going to multiply it by this, let's say the loading factor of, this is the input resistance of the downstream circuit, which is 3 kilo ohms, divided by the same 3 kilo ohms, plus the Thevenin resistance of the upstream circuit, which is 2K parallel 1K is 667 ohms. Okay, so we take 6 volts, so we predict VA is 6 volts times 3 over 3.667. See, on the previous page we had 300 over 300.667, which was very close to unity. But now here we have 3 over 3.667. 3 over 3.667 is a factor of 0.8181. So it's about a 20% effect. Factor of about 0.82. So this is so this is 6 volts times 0.8181, which is 4.91 volts. Okay, so we expect VA to be 4.91 volts, and then we actually expect VB to be 2/3 of VA. So that's 3.27 volts. So since there's nothing except maybe a voltmeter whose input resistance is huge, it's 10 mega ohms, connected at the output of B, we can just use the simple voltage divider relationship to relate the voltage at A to the voltage at B. So the voltage at B is just 2/3 of the voltage at A, just using the simple voltage divider equation. Let's see what we get when we wire this up. So I need to find another 1K resistor in the drawer, and I need to find another 2K resistor in the drawer. Here's a 2K, red, black, black, brown. So that will replace my 100K resistor here. And then here's a 1K, brown, black, black, brown. That will replace my 100K resistor here. So you might notice that when I unplug the downstream circuit, I get 5.99 volts. So I guess the reason that's at all different from 6 volts is presumably just the 1% tolerance of these parts. See, here's where if you do measure things, at the 1/10 of a percent level or better with your ohm meter, you can reach more incisive conclusions. So this is the counter argument to my story from the previous lab about being content with the nominal values of components. If you really want to see the difference between a factor of unity and a factor of 0.9977, in other words 300K over 300.667K, you need to do better than 1%. But for the purpose of this lab exercise, I'm content to say that on the first page, at the 1% level, the output of the circuit is unchanged, whereas on the present page here, we have like a 20% effect. Okay, so I'm going to wire up this 1K resistor, and then I'll run this 2K resistor down to ground, and lo and behold, we see 4.90 volts. It says 4.897, so I'll call that 4.90. So we observe 4.90 volts, and then 3.2699, so that's 3.27 basically. So here we observe 3.27 volts. Okay, so cool. In making, okay, so it is definitely worth your taking the time to make sure you follow why on this page we both predict and observe values that are about 20% smaller than the values that we both predicted and observed on the first page. So if this downstream circuit has an input resistance which is, let's say 2 orders of magnitude bigger than the output resistance of this upstream circuit, output resistance is a synonym for Thevenin resistance, then the presence of this downstream circuit basically doesn't affect the output of the upstream circuit. But when the input resistance of this downstream circuit is, comparable to, basically the same order of magnitude as the output resistance or Thevenin resistance of this upstream circuit, then we have to work harder. So then we have to figure out what is this factor in parentheses that I like to call the Thevenin factor or the loading factor. If you find out the official name for this factor, please let me know. So this is a point that is absolutely worth understanding. It will come up again and again in the course. Now, in making your voltage measurements in the previous 2 parts of the lab, parts 1.1 and 1.2, you probably neglected the finite 10 mega ohm input resistance of the voltmeter. Why does that make sense? Well, so in the case where this is a 1K resistor and this is a 2K resistor, so it's the voltmeter at point A on either the first page or the second page, or it's the voltmeter at point B on the second page, this Thevenin factor, or the loading factor, is 10 mega ohms over 10 mega ohms plus 667 ohms, which differs from unity at the 10 to the minus 4 level. Okay, so to about 4 decimal places, this is just a factor of 1. So that's why we didn't worry about it. Our voltmeter only reads out 4 or 5 digits. So in the case on the previous page where this was a 100K and this was a 200K resistor, this becomes 67 kiloohms. So that's 10 mega ohms over 10 mega ohms plus 67 kiloohms. So 100K parallel 200K is 67K. And that is a less than 1% effect. So it's about a 2/3% effect, a little less than 1% effect. So it's comparable to the tolerance on our resistor values. If we really wanted answers at the 0.1% level, we would have actually had to account for the 10 mega ohm input resistance of the voltmeter when probing point B on this circuit. So if we really wanted to record everything with, say 4 decimal places and make predictions and comparisons at that level, the 10 mega ohm input resistance of the voltmeter to probe point B actually would have mattered. But again, we're interested in things at sort of the few percent level in this course in most cases. And if we ever want something at the 1% or better level, we'll say so explicitly. So when probing the output of a 1K, 2K voltage divider, it absolutely made sense to treat the voltmeter as if it were ideal, treat the input resistance of the voltmeter as if it were infinite. But actually, when probing the output of this 100K, 200K voltage divider, it only made sense to neglect the input resistance of the voltmeter because we were looking for effects about 1% or larger. So if we were actually looking for 0.1% effects, then we would have had to take that into account. So on reading through this question is actually more interesting and subtle than I originally intended when I wrote it down. So a rule of thumb for voltage sources is that the source resistance, aka Thevenin resistance, aka output resistance of the upstream circuit needs to be much smaller than the input resistance of the downstream circuit, aka the load, if you want the source voltage to be relatively unaffected by the presence of the load. By the way, the opposite is true for current sources. We won't use current sources very often, but whereas a voltage source prefers to see a very large load, a current source prefers to see a very small load resistance. So the advantage of following this rule of thumb is that it allows you to consider the parts of a complicated circuit individually. Alternatively, keeping in mind R Thevenin for the upstream circuit and R input for the downstream circuit allows you quickly to calculate or approximate this so-called Thevenin factor or loading factor, right, which is R in of the downstream thing divided by R in of the downstream thing plus R Thevenin of the upstream thing. Okay, so with that in mind, look at but do not build the circuit drawn below. What is the ratio of V in to V out, or maybe V out to V in? Well, stare at this for a moment, maybe pause the video, but notice that this is a 2-to-1 voltage divider, and then this uses much larger, like 30 times as large resistors, and this is a 2-to-1 voltage divider, and this uses much larger, like 30 times as large resistors, and this is a 2-to-1 voltage divider, and this uses like 30 times as big, much larger resistors. This is a 2-to-1 voltage divider. So we have 1, 2, 3, 4 2-to-1 voltage dividers connected one after the other, and in every case the input resistance of the downstream device is about, well, let's see, this is like 600 divided by 5. So in every case, the input resistance of the downstream circuit is about 100 times the Thevenin resistance or output resistance of the upstream circuit. So at the kind of percent-ish level, V out must be 1/2, 1/4, 1/8, 1/16 of V in. So I would say V out equals 1/16 of V in at the kind of percent level. Yeah, it's probably at the few percent level in this case. So at the kind of few percent level, let's say V out is just a 1/16 of V in. By the way, if instead all the resistors were the same, then you could not just do this in your head. Actually, there was a guy in the office next door to me remarkably was able to do this in his head. But you can't really do this in your head, because then you would have basically like a kind of on the order of 25% Thevenin factor at each stage. You see, because you would have 1K, 1K, and then you'd have a 2K load, and you'd have 1K, 1K, and a 2K load, and so on. So I think you would have roughly like a 20%-ish Thevenin loading factor at each of these 3 points. So you would probably have to do some pencil and paper math to figure out what V out was as a fraction of V in if all of these resistors were identical 1K resistor. Because we did not obey the simplifying, we would not in that case have obeyed the simplifying rule of thumb that each downstream subcircuit has an input resistance which is much, much larger than the output resistance or Thevenin resistance of the upstream circuit fragment. So following that rule of thumb makes circuit design easier because you don't have to think too hard about the effect of the downstream circuit on the output of the upstream circuit. Now, for part 2, we're going to find a pair of 10 mega ohm resistors in the back room. So I will go do that. So these are both old-fashioned 5% tolerance. The gold stripe means 5% tolerance. These are old-fashioned 5% tolerance 10 mega ohm resistors. Brown, black, blue. And then the gold stripe means 5%. So what is blue? So we say black, brown, R, O, Y, G, B. So blue must be 6. So that is 106, or 10 times 10 to the 6th power. So that makes sense, 10 mega ohms. Let's measure them with one of our ohm meters. So let's pick up this digital multimeter and put it into ohms mode, and the red wire is in the ohm or volt measuring position. So the first one measures 10.4 mega ohms basically, 10.4, maybe 10.5 mega ohms. The second one measures a little less than 10.4 mega ohms. So they're both about 10.4 mega ohm. Okay, so we're going to build a new voltage divider using this pair of 10 mega ohm resistors and using an input voltage from the power supply of 20 volts. And we want to measure the current through the divider using the DMM as an ammeter. Let's try that. So let's unplug our previous circuit. So here's the power supply positive voltage coming in, and here's the power supply ground. So we'll put one of our, initially, okay, let's put one of our 10 mega ohm resistors between power supply voltage and this node, sort of like our usual node A, and then we can put the other one between that node and ground. That would be a voltage divider whose output voltage should be half of the input voltage. But okay, we're told we want to measure the current. So to measure the current, I think we want to put the ammeter like this. So here is our supply voltage, and we'll put the ammeter here. And then we have one of these 10 mega ohm resistors, and then we have the other 10 mega ohm resistor. And here's ground, and this is our output voltage. So to do that, I want to move this upper resistor so that it's now between two different nodes on the breadboard, and then we can take a current meter. Here, let's use this Amprobe 37XR current meter. This is the one that all of the lab write-ups tell us has a series resistance of 10 ohms, I think in the milliamp or microamp scale. So I'll unplug the red wire from the volts and ohms receptacle, and I'll put it into the milliamps and microamps receptacle, and then I'll put this on microamps mode, because I think with such huge resistors we're expecting currents no bigger than microamps. Okay, then we'll use the current meter to complete the circuit. So we'll go from this supply voltage to this intermediate breadboard point. And I think I'm actually going to spread things out a little bit more on the breadboard so that it's a little bit easier for you to see what is wired where. Okay, we have the positive power supply lead going in here. We have the red current meter lead in that same row. And we have the black current meter lead in this breadboard column, and sharing that breadboard column is the left side of first resistor, and then the right side of the first resistor and the upper side of the second resistor are in this breadboard node, which is like our circuit's output, and then the lower end of that second resistor, the second 10 meg resistor, goes to ground, and then ground goes back to the black lead of the power supply. Now it turns out I still had the power supply set for 9 volts the whole time. I guess if I turn it off, I see it says 0.05 microamps. I think that's just the meter. See, I unplugged the power supply completely. It still says 0.05 microamps. So I think that's just the precision of the meter. Now let's go to 20 volts. 20 volts. Turn it on. So this says 20.00 volts. And I see 1.02 microamps. Okay, so this reads 1.02 microamps. So 20 volts divided by 20 mega ohms is 1 microamp. So this 1 microamp reading does make sense. Okay, measure the current through the divider by using DMM as an ammeter. How did you do it? Is the answer what you expect? So I think yes. So we expect, so if this is 20 volts, then we expect the ammeter to read 1 microamp, and that is what we see. Now use the multimeter to measure V out. Whoa! What do you read? Okay, let's try that. So this other meter we're going to put on volts mode, and the red wire is in the ohms and volts position. Okay, and it just, basically you can see just noise on the lowest digit when there's nothing plugged in. Okay, so I have my little leads here on the voltmeter, so I'll plug the black end into ground, and I'll plug the red end into the output of this voltage divider. I think we want to keep an eye on this current also. Oh, I plugged into the wrong node on the breadboard. Okay, here. So, the current went up from 1 microamp to 1.33 microamps. That seems suspicious. And then, whoa, that's really weird. Our voltmeter, instead of measuring 10 volts as expected, our voltmeter measures 6.625 volts. But there's a hint. You see, our current meter went from reading 1.0 microamps to reading 1.33 1.36 microamp. What happened? Well, I think we know what happened. So the circuit that we really have here now is there is a voltmeter here, but the input to the voltmeter has a 10 mega ohm resistor in parallel with its input. So the voltmeter looks like a perfect voltmeter in parallel with a 10 mega ohm resistor. So if we take that into account, then we have, well, the easiest way to look at this is to say this is 10 mega ohms, and down here what we see, the voltage we see at this node is given by the voltage divider relationship, where this is 10 mega ohms and these two resistors in parallel form 5 mega ohms. So if that's 10 and that's 5, we should get 1/3 of 20 volts. And 1/3 of 20 volts is indeed 6.66 volts. So that makes sense. We see 1/3 of 20 volts. And I think this should also make sense, because now instead of 20 volts divided by 20 mega ohms, we should see 20 volts divided by 15 mega ohms. 20 volts divided by 15 mega ohms is 4/3 of a microamp, and 1.36 seems compatible with 4/3 of a microamp. Draw the circuit that includes the meter's input resistance. Well, I guess I did that up here. Using your diagram, are you able to explain the meter's reading now? Yes, check. This is an example of one of those unusual cases in which the meter's very large but finite 10 mega ohm input resistance must be accounted for. Okay, well that was cool. Now let's do the oscilloscope function generator tutorial. You're just going to watch me do this today. You don't have to write anything down. And then you are going to do it yourself in person in the next lab, our first in-person lab. So my hope is that you're watching me do it first might speed you up when you do it yourself. I've never done this scope tutorial, so we're all going to learn something here. The function generator and oscilloscope are general purpose instruments that are used in a range of fields, blah, blah, blah. Okay, you definitely want to know how to use these things. These are going to be some of your most important tools for the rest of the semester. The oscilloscope here will basically be your eyes for seeing what's going on in the circuit. And this function generator will be your mechanism of providing the circuit under test with a known input signal so that you can see whether it behaves in the way you expect. Turn on the power of the function generator and the oscilloscope. So function generator has a power button over here. So if I push the power on button on the function generator, I guess you'll see the lights blink a little bit. Okay, then after adjusting the brightness a little bit to make it more visible to the camera, you can see that this thing reads 1.0000000 kilohertz. Okay, so I guess it really means it, 1 kilohertz. And this thing says sine wave. And there are two outputs, and neither one of these green lights is on, so both outputs are currently disabled. All right, so turn on the power of the function generator. Now let's turn on the power for the oscilloscope. Okay, so here is the oscilloscope power button down here. I'll push that. Okay, we see some lights blinking, and then there are a whole bunch of cables here. I'll pull these cables out of the way. Okay, so you can't read what the screen says, but it says power on self-test path. Okay, and we have the 4 channels worth of oscilloscope probes plugged in. I think probably for our first exercise we're supposed to use a coaxial cable instead of a scope probe. So these are oscilloscope probes. You'll become familiar with them later in this exercise. Connect a coaxial cable from channel 1 of the function generator to channel 1 of the scope. Okay, this requires going into this box and finding this is a coaxial cable. Okay, so we're going to take a piece of coaxial cable. Now what's a little confusing here, channel 2 is on top, channel 1 is on the bottom. That's always a little bit of a source of confusion. So here's channel 1 on the bottom, and then I'll unplug this scope probe from channel 1, and I'll plug the coax cable into channel 1. Press sine on the function generator. Read across the top of the function generator display. You should see from left to right. Sine, high Z, channel 1. High Z means the display of the function generator is set to report parameters of waveforms, assuming the function generator is connected to a device under test with a large impedance. You'll understand what that means later. Read the frequency and the amplitude of the sine wave by pressing the blue buttons under the function generator display. I see. See, here is frequency, 1 kilohertz. Oh, period, 1 millisecond. See, push it once, it says 1 kilohertz. Push it again, it says period 1 millisecond. Okay, so that's a 1 kilohertz. Amplitude, 5 volts peak to peak. Oh, that's interesting. High level, low level. Okay, I like amplitude better. Amplitude 5 volts peak to peak. Offset 0 volts DC. Phase 0 degrees. Oh, this is like, I think this aligned phase means it aligns the phases of channel 1 and channel 2 if you're using both outputs together. Change the frequency to 2.8 kilohertz. 2.8. Aha, this button's labeled kilohertz. 2.8 kilohertz. Okay, so the frequency 2.8 kilohertz. Then change the frequency to 1.0 kilohertz using the knob and the arrow keys. I see. Okay, so I guess if I turn the knob counterclockwise, you see I can move this first digit, but I guess I want to move the second digit instead. So there we go, 1 kilohertz. So you can choose which digit you move with these arrow keys. Remember, we set the frequency to F, which is 2 pi omega, has units of cycles per second. Oh, enable the output of the function generator. To do this, you push the button called output. So this is for channel 1, and this one is for channel 2. We're using channel 1. So, okay, now the green output enable for channel 1 is illuminated. Oh, now we're going to go to the oscilloscope. Now, the instructions say press the auto set button. Now, I should point out that for pedagogical reasons, I am supposed to discourage students from making frequent use of the auto set button. But the auto set button can be useful if you're completely lost or if you just want the scope to try to set itself up. So this black button is the auto set button. Let's push the auto set button and see what happens. Oh, well, I guess that yellow trace on top is our sine wave, and I'll bet we could even make it go away by turning off this output. Oh, look at that, it went away, it came back. Okay, that's cool. And then we have, I guess, the cyan or light blue, channel 2, and we have the magenta or pink, channel 3. Let's follow the direction. The function generator signal should be displayed on the scope screen. The scope vertical voltage scale, volts per division, and horizontal time scale, time per division, are shown on the scope display. Do they make sense? Well, if we zoom in a little bit, this says 5 volts per division for channel 1, the yellow channel. And so if this is 5 volts per division and our amplitude coming out of the signal generator is 5 volts peak to peak, then if we move this trace down, you'll see how in a moment, then it does seem as if the peak to peak voltage is 1 division. So there are little white graticules. There's basically a little grid. So this is the top. There's 1 grid point, 2, 3, 4, 5, 6, 7. So there's a little vertical grid that you can just barely see on the screen. It's clear to me, but the camera doesn't pick up the contrast so well. Okay, I think maybe now you can see more clearly that the peak to peak amplitude is 1 grid spacing vertically, and this 5 volts indicates that this is 5 volts per division, so each vertical box should be 5 volts. And that makes sense because the output waveform has an amplitude of 5 volts peak to peak. This is different by a factor of 2 from the conventional mathematical definition of the amplitude of a sine wave. So this says amplitude is 5 volts peak to peak. So peak to peak is supposed to make it clear that we're not talking about the number a in front of a times sine of omega t. You're really talking about the maximum minus minimum. Okay, then the horizontal time scale. So if you can read it, this says 400 microseconds. So this says 400 microseconds. So each horizontal box is 400 microseconds. That's not terribly helpful because you know the period should be 1 millisecond. So I guess it tells you the period should be 2.5 boxes horizontally. And I guess we go 1, 2.5 boxes. That sort of makes sense. Okay, so I think we understand that. Do the values of amplitude, voltage, and period time displayed, do they make sense? Yeah. So, all right, we said 5 volts peak to peak amplitude. So the function generator and the oscilloscope agree on that. And if we go to frequency, we see 1 kilohertz frequency, or we push frequency again, we see 1 millisecond period. And that makes sense because if this is 400 microseconds per horizontal division, then 1, 2.5 horizontal divisions would be 1 millisecond. So I think that makes sense. On the function generator, press square to output rectangular pulses. Okay, square. Observe the change in the waveform. Did the frequency or amplitude change? Well, I would say the amplitude is still 5 volts peak to peak, and I think the period is still 2.5 boxes. So if we start from here, here's a period, so 1, 2.5 boxes, so that makes sense. So I would say no, the frequency and the amplitude did not change, but now we've gone from a sine wave to a square wave. Now press ramp. Oh, ramp. Oh, that's a kind of a triangle wave. Press the blue button under the sim label on the function generator display. Oh. And vary it from 0 to 100%. So I'm going to move this digit to the left so that I can quickly change the most significant digit. So let's go down to 0. Okay, so I guess for 0, I always get the down-going part. So the up-going part of the triangle wave is instantaneous. And then we can go gradually up, and there's 90%, 100%. Okay, so for 100%, then now the down-going part of the triangle wave is instantaneous, and the up-going part is 100%. So I guess this indicates what fraction of the waveform is the upgoing versus downgoing part. So there we can go back to 50%. Return the function generator channel 1 to a sine wave with frequency 1 kilohertz and amplitude 5 volts peak to peak. So here's a sine wave. Oh, okay. Go to frequency 1 kilohertz, amplitude 5 volts peak to peak. Okay. Connect the coax cable from channel 2 of the function generator to channel 2 of the scope. To do that, I reach into the box and I find another coaxial cable. So it has these so-called B and C connectors on the end. So I'll take this coax cable and I'm going to go from channel 2 on the function generator to channel 2 on the scope. Okay, so that's all plugged in. So here's my first coax cable, here's my second coax cable. Okay, press channel 1, channel 2 on the function generator. So that toggles the display between channel 1 and channel 2. So now we're looking at the parameters of channel 2. Take note of the default waveform frequency and amplitude. It seems like it powered up to a ramp, which is 1.5 kilohertz in frequency and 5 volts peak to peak amplitude. I'm not sure that's anything so profound. Change channel 2 to output a sine wave with frequency 1 kilohertz and the same amplitude as channel 1. So sine frequency 1 kilohertz. Okay. Press view on the function generator to toggle between different views of the active channel. Oh, that's interesting. So it says, see, that's supposed to look like a sine wave. Oh, that's interesting. Oh, I never even knew that button existed. So now I can see what's going on in channel 1 and 2 at the same time. That's interesting. I learned something new. So I never knew what the view button did before. And I've been using these function generators for probably 6 or 7 years. Output channel 2 by pressing output. Okay, here's the output button for channel 2. Oh, gee, okay. Now you see, on the oscilloscope, channel 2 is set to 100 millivolts per division. So it makes sense that the waveform is going off scale. In the vertical block on the oscilloscope panel, press the blue button. Okay, if we press the blue or cyan button, now channel 2 becomes the active channel. So if we press the blue button again, channel 2 goes away. And then we press the blue button and we see channel 2. And actually I could press the channel 3 button, and now channel 3 becomes the active signal, but there's nothing going into channel 3. And I push it again and it disappears. And it's kind of useful to make it disappear because there's nothing plugged into it. So you see I can make channel 2 active, and then I can make channel 2 disappear, and then I can make channel 2 active again. Turn the knob under the blue button to 1 volt per division to observe the full signal. Okay, so we'll turn this knob. So that's 200 millivolts per division, 500 millivolts per division, 1 volt per division. So then it should be 1 2.5 boxes up, and then 1 2.5 boxes down. I think that makes sense. Press the yellow button, channel 1, on the scope. Here we go. So now you see, notice that this is filled in, so you can see that it's the active channel. Watch the 1 and 2 arrows on the left as I push the 2 button, the 1 button, the 2 button, the 1 button, the 2 button, the 1 button. So you can see the active channel has the filled in symbol on the left. Coupling, DC, AC, and ground. DC coupling is used most often. The full input signal is displayed on the scope. When AC coupled, the scope only sees the AC signal. You will use this setting when you're trying to measure the details of a small AC signal superimposed on a much larger DC signal. Okay, so that's DC, that's ground. Okay, there's DC, there's AC, there's ground. So ground just says it connects channel 1 to a ground. So that's really not very useful unless you're trying to ask yourself, what does the scope think it sees when there's a 0 volt input? There's DC. So you'll see when we study capacitors that what AC coupling mode does is it puts a large capacitor in series with the input, and that has the effect of blocking any DC component while permitting an AC component to get through the capacitor. So intuition would say when you're looking at an AC signal you want to use AC coupling. That's not a correct statement. You almost always want to use DC coupling. The only time you want to use AC coupling is if you're trying to observe a very small time varying signal which is resting on top of a large constant offset. You should continue reading through the text here on page 7. I won't read it out loud. So here's a really important point. Common lab signal sources, such as our function generator, have an output source impedance, in other words, an output Thevenin resistance of 50 ohms. This can cause some confusion, which is discussed further below. That's good to know. And by the way, 75 ohms is a standard which is often used with cable television, but it won't be used in our course. So let's notice that if we set the channel 2 scope input termination, right now it's at 1 mega ohm. If we set it at 50 ohms, oh sorry, I'm looking at channel 1. Let's push the channel 2 button. If we change the channel 2 termination from 1 mega ohm to 50 ohms, notice that the amplitude goes down by a factor of 2. And that makes sense. Remember, in the previous lab, we saw that if you connect a load resistance, which is equal to the Thevenin resistance of the voltage source, then you reduce the amplitude of the observed voltage by a factor of 2. So we've basically done that here by changing the input resistance of the scope input from a mega ohm to 50 ohms. Now we can go back to a mega ohm, and you can see that it's back to the 5 volt peak-to-peak expected amplitude. So this is a key point. A constant source of confusion is the output impedance setting on the function generator. I think we can get there by saying utility channel 1. You see there's high Z, or 50 ohms. We do 50 ohms and we go back to the display, then it thinks now it reports an output of 2.5 volts peak-to-peak. But notice that the channel 1 waveform, now it's 1 volt per division, so it's still, here, let me offset it so that it starts and ends on a box 1, 2, 3, 4, 5. So it's still actually 5 volts peak to peak, but the function generator reports 2.5 volts peak to peak because it is reporting what would be observed by an observer whose input resistance is 50 ohms. So if we then set the scope termination on channel 1 to 50 ohms, now we will see 2.5 volts peak to peak. So you can see it goes up by 1.25 boxes and it goes down by 1.25 boxes. So we get that if we tell the function generator to interpret what it's sending as if it is sending it into a 50 ohm termination, and you tell the scope actually to offer a 50 ohm termination. That's not what we will use in this course. In this course, we will always set the scope to a mega ohm termination. Let me just make sure that's true for both channels now. And we will always tell the function generator to, we don't want invert. Invert flips the sign of the output. You see, it actually changes the output to be Well, you can't really tell with the sine wave, but it changes the sine wave to be upside down, basically. We don't want that. So if you push this load button multiple times, it goes between 50 ohms and high impedance. It's not actually changing the output impedance of the signal, it's changing the function generator's interpretation of what it is outputting. That's pretty tricky. So you always want to be sure that your function generator is in high impedance mode. And you want to be sure your scope inputs are in high impedance mode. And then if you get a disagreement by a factor of 2 between the function generator and the oscilloscope about the amplitude, you should believe the scope, not the function generator. So there's the invert button. So I was just pressing that a moment ago. So let's go over to utility. Oh, sorry, there's an invert button on the scope. There's also an invert button on the function generator output. I don't think you'll ever use that. But it turns out there is this normal invert button on the function generator. Again, I'm pretty sure you will never ever use that. The scope has an invert button. Okay, here's the invert button on the scope, and you can see it basically just flips the sign of the display. So it interprets its input waveform as if it had a minus sign in front of it. Similarly, if we push the blue button, and now we push invert, we can flip the sign of the blue trace, go back to the yellow channel, and we can push the invert button. We flip the sign of the yellow trace. So we can also disable channel 1 by pushing this yellow button, and we can disable channel 2 by pushing this blue button. First you push it once to make that channel the active selected channel, and then you push it again to remove that channel. So we can push 1, and we can push 2. If I push 2 again, I think it will disappear, and then I push 2, it reappears. To make channel 1 disappear, I have to push it once to make it the active channel, and then push it again to make it disappear. So if a given channel is the active channel, then pushing that channel's button, 1, 2, 3, 4, will make it disappear. And then if it's not displayed, it will make it appear. Now we can turn the scale knob over here. So this knob says scale, and I can turn it clockwise, and now see, this said 400 microseconds per division. Now it says 200 microseconds per division. Now it says 100 microseconds per division. I think we actually want to go counterclockwise. 200, 400, 1 millisecond. So now the horizontal timescale is 1 millisecond per division. And this makes more sense. You can see that the period of each sine wave is 1 grid unit horizontally. Now let's press the acquire button on the scope, and then we can press the button under the mode info tab on the screen. So this mode, it says sample. And now we get a menu over here, which is a little hard to read. But this says sample. Well, then we can select, I guess we could select peak detect. We could select high res. For reasons I don't understand, high res always gives you a smoother waveform than sample. Next, select average. So we'll select average, and I think it's averaging 512. I guess it's hard to read it might be hard for you to read, but this says average 512. The number of traces can be varied using the multi-purpose. Here's the multi-purpose A knob. So I can increase the number of, 512 is the maximum, I guess, on this mode. We can go down to averaging 2, and then we can go up. Here's averaging 4, averaging 16. So I think if we go from averaging 2 to averaging 512, you should see that the curve gets a lot smoother, because it's like taking a statistical average of a larger number of samples. And we can go back to sample mode, it's pretty fuzzy. Go to average mode, it's pretty smooth. I generally don't like to use average mode because it's easy to confuse yourself. Like you can think you see something which is stable, but it's actually not stable. So it says reset the function generator back to 1 kilohertz 5 volt peak to peak amplitude. I think this has been true all along. So here is channel 1 kilohertz 5 volts peak to peak, and then I guess we could go to channel 2 and it's 1 kilohertz 5 volts peak to peak. So I think this has been true all along. Select high res on the scope. So here's high res. High res is a variation of sample. The scope acquires more sample points than the displayed points on the screen. High res averages a fixed number of neighboring points for each trace and displays a smooth average of that trace. This reduces the input signal bandwidth but displays a nice smooth signal. So I like high res. High res is my favorite mode on this scope. And I think, see, if I change the scale horizontally, then you can see a big difference between the fuzzy sample mode and the nice smooth high res mode. So I like high res mode. Next, turn on the XY display mode on the scope. Okay, XY display is here. So we're going to say on Oh no, actually, okay, XY display, triggered XY. Okay, make sure the volts per division are the same on channels 1 and 2. They are. Press the blue button under align phase on the function generator. Okay, here is align phase on the function generator. Oh, now we have a straight line. This sets the output of both channels of the function generator to be in phase with one another. Do you observe a diagonal trace with a slope 1 on the scope? By the way, if you ever studied like linear versus circular polarization of light, this might be familiar. We have these sine waves, which could be exactly in phase with each other, or could be out of phase. In the XY mode, the horizontal axis is the input signal on channel 1, the vertical axis is the input signal on channel 2. So I think that makes sense. So now they're perfectly in sync with one another. Now vary the phase on the function generator. So let's vary the phase on channel 2. So I'm going to go to channel 2, and I'm going to vary its phase. So here, there's 1 degree. So if I make, see there's 5 degrees, 8 degrees, 10 degrees. See, now I'm basically turning a linear polarization into a circular polarization. 30 degrees, 45 degrees. I think 90 degrees should give us a nice circle. Let's see what happens when we get to 90 degrees. So then we'll have, yeah, basically a sine and a cosine. So you see, so this is like the horizontal axis is the cosine and the vertical axis is the sine, and you get a nice circle, and so on. I guess if we go to 180 degrees, I think we'll get a straight line with the opposite slope. Let's try that. Yeah, now they're perfectly out of phase with one another, so we see the y is just the negative of x. I like the 90 degree. Okay, there we go. A nice 90 degree circle for perfect circular polarization. If you set the function generator channel 2 with different integer multiples of channel 1 and vary the phase, you can get kind of cool Lissajous displays. Let's try that. So we can do frequency. Here, we'll make this 2 kilohertz. Oh, that's pretty cool. 3 kilohertz. Wow. 5. Oh, that was 4. I see. So yeah, 2. There's 1, 2, 3, 5, 7. Huh. That's pretty cool. I guess nowadays you could just ask Mathematica to graph this for you. By the way, you might notice that we go up to a higher frequency and then back down to 1 kilohertz, and we get kind of a different result every time we go back to 1 to 1. And that's because having momentarily changed the frequency of channel 2 to be different from that of channel 1, now we have messed up the phase relationship. So if we do align phase again, then we get the nice circle relationship again for 90 degree phase offset. I guess we could do 0 degrees, and then here we can go frequency. So there's 2, 3, 4. Okay, so I guess every time you change the frequency, I think you want to do align phase so that they both start at the same time. Anyway, that's kind of fun, although I think it's even more fun just to do it in Mathematica. Now, turn off the XY mode. So now we're back in ordinary. Well, that's interesting. See, now we have these perfect waveforms overlapping, so you can only see one at a time. And I can toggle back and forth which one is on top of the other. But if I offset them vertically by just a little bit, then you can see that there are 2 traces there. Trigger block. This is the most important part of this tutorial. You basically can't use an oscilloscope without knowing how to trigger it. By the way, if you think of the oscilloscope as a camera that you set up on the side of a road, which is capable of recording, let's say, a few seconds of video, then the trigger is like some kind of a radar-based device that tells the camera to start recording. So a properly designed trigger lets the camera see things that are interesting when they happen and allows the camera to ignore times when nothing at all interesting is happening. In this course, we're often looking at repetitive waveforms, so it doesn't make very much difference in that case exactly when the scope triggers. In real life, often you want to catch something that happens only once in a while, and then the trigger is much more important. Anyway, back to the text. Turn off channel 2 on the scope, so you were just looking at channel 1. Okay, so to do that, we will push the channel 2 button so that it becomes active, and then we'll push the channel 2 button again, and channel 2 disappears. Channel 1 should be a sine wave with frequency 1 kilohertz and 5 volt peak-to-peak amplitude from channel 1 of the function generator. I guess while we're here, we can turn off channel 2 of the function generator. This does appear to be a 5 volt peak-to-peak sine wave, and I'm going to change the horizontal scale to 1 millisecond. Then it is very obvious. See, I can move the horizontal position which makes it easy for me to see from the zero crossing that the period is indeed one horizontal division. I could change the vertical position so that the top and bottom of the waveform are clearly 1, 2, 3, 4, 5 divisions apart, though it's more conventional to have the zero of the waveform happen in the middle of the display. The scope continuously records the input signal and stores a record of it. The scope displays these data when the signal satisfies the conditions specified by the trigger. In the default setting of the scope, the trigger event occurs when the trace is at the center of the screen, so the display shows the input signal before and after the trigger condition is satisfied. The trigger location is displayed as a T on top of the scope display. If this T is not in the center of the screen, okay, ask for help. Now, it is possible to set things up so that the trigger is way off to one end of the record, because the record that's actually recorded by the scope can be, well, in this case it's 10,000 points, and I think this scope is actually capable of recording hundreds of thousands of points, maybe even millions. So it is possible that the trigger position is way out of view, and I think that's what this top thing is for, so that you can get some sense of where the trigger is with respect to the length of the record. But I use so many different types of oscilloscopes from day to day that I don't always remember precisely which features which scope has. They're all very similar, but each type of scope has its own personality that you need to get used to through using it for a while. Okay, anyway, things are as the instructions say. The trigger position is in the middle of this. Push the menu button on the trigger menu of the scope. So this is the trigger menu. This little box here contains things relevant to triggering. So we'll push the menu button. Now we see the trigger menu. This brings up several trigger setting options that are shown at the bottom of the display. The rightmost option should be mode. It should be set to auto. Okay, here is mode. And indeed, auto is almost always what you want. Sometimes you want normal. Normal means if a trigger doesn't happen, the scope will not update. Auto means that if you don't see a trigger for a while, you just issue a trigger even though the trigger event didn't happen. So auto is much more helpful for finding your way around when you don't yet know what you're looking at. Normal is often much more helpful once you already know what to look for and you want to focus on that. But I'm going off-piste here. Select the right-hand button that corresponds to auto untriggered roll. That is what is already selected. You will usually want to use the scope in the normal trigger mode, which we will study below. That's true. Once you know what you're looking at, normal tends to be more useful. But when you don't yet know what you're looking at, auto is more helpful because it allows you to get the scope set up even if the scale, even if the waveform that's actually coming into the scope is not at the position that you think it is at. If the scope is triggering, you should see a trace and you should see run in the uppermost left-hand corner of the display. Oh, I see. Well, here is run and triggered in the upper right corner of the display. Vary the level knob in the trigger block. Okay, here is the level knob. So we can bring the level knob so you can see this horizontal yellow line corresponds to the voltage at which we trigger. So the scope triggers when the input signal goes from just below the yellow line to just above the yellow line. That's called a positive edge. In fact, this is slope, so that's a positive edge. You can actually push slope and trigger on a negative edge instead of a positive edge. So if I increase the trigger level to be above the maximum level of this waveform, then the scope never triggers, but now it says auto. So you can see that now when the scope decides to read out has nothing to do with when the waveform passes by. So then the phase of the displayed waveform is random. Notice as you increase or decrease the trigger level, the trace shifts left or right so that the signal at the trigger position matches the trigger level. Right. Move the trigger level outside the signal range, which is what we just did. That is, set the trigger level to a voltage that is larger than the peak voltage of the signal. In this case, this corresponds to a trigger level larger than 2.5 volts. That's true. We're triggering at a trigger level now of 2.9 volts. And you can see where the trigger is if you... So I think this horizontal line goes away after a few seconds, but you can see, okay, it's at 2.84 volts, and then the line went away when we stopped adjusting it. In auto mode, a trace will still be displayed, but it will be jittering in the horizontal direction. In other words, the phase of the signal is unrelated to the time at which the trigger happens. Return the trigger level close to 0 volts. Actually, I think I can do this. Push to set to 50%. I see. Then it automatically puts the trigger level sort of in the middle of the range. I think it's the middle of the waveform. Yeah, I'm pretty sure this 50% means the middle of the waveform rather than the middle of the window. I guess we could, I'm going to go off script again a little bit. I'm going to add a little vertical offset. I will add a 1 volt, oh, I see. Okay, so I've been looking at the channel 2 menu, so I'll push the channel 1, channel 2 button. Now I'm looking at the channel 1 menu. I'll do offset, and I'll say 1 volt DC. Okay, so now I have a 1 volt DC offset, and I can push the trigger level button, and it says push to set 50%. Aha! So it sets the trigger level for 50% of the observed waveform. That's convenient. Okay, that's what I thought it would do. So it must look at the high and low values of the observed waveform, and then it sets the trigger level to half of that. I guess that's a convenient thing to do if you don't initially know what trigger level to use. So now I will remove this 1 volt offset, 0 volts DC. Okay, and then I'll move the trigger level back down to 0. Okay, push menu in the trigger block. I think we want to, yeah. So the menu went away, now we want to bring the menu back. There's the trigger type. We almost always want to do an edge trigger. So that means it's like you're crossing a low to high threshold, or you're crossing a high to low threshold. There are other types of trigger conditions, which can be quite powerful for tracking down infrequently occurring glitches in digital systems, or systems that have enough intelligence to be able to do something only once in a while. But it will be pretty rare. I don't think in this course we'll ever use a type of trigger other than edge. Okay, the source tab. So our trigger source is channel 1. See, if we were to change the trigger source to channel 2, I think it says A, so I think we turn knob A. So then we can change the trigger source to channel 2, but I guess our channel 2 sine wave is off. I could turn channel 2 back on, and then it's triggering on channel 2, but we don't see channel 2. This might just confuse you. Or if I try to trigger on channel 3, you're triggering on something that there's no input going into, so then it doesn't make any difference what I do over here. So you have to be a little bit careful that you know which channel you're triggering on. It's pretty easy to get confused if you're trying to look at channel 1, but the trigger is looking at channel 3, and if those two signals are unrelated to one another. So the trigger is able to decide based on any one of these input channels, or even some additional inputs, like this is an auxiliary trigger input. I think it's also possible to trigger on you can trigger on the 60 Hertz line voltage from the electrical mains if you want to. So this is one thing you need to check. Which channel, which input signal is the scope trigger looking at to decide when to trigger the scope. And again, triggering the scope is sort of like pushing the shutter button on the camera. Then the coupling information tab displays trigger coupling options. DC coupling is used most often. So once in a while, you might want to use AC coupling. It's sort of under the same circumstances as you would use AC coupling for the display. We might see an example of that later. It's basically if you have a small sine wave that you want to be able to see clearly, and that small sine wave is on top of a large constant DC voltage. That's the most common case for using AC coupling. So normally you'll use DC coupling. If the signal is noisy, selecting high frequency reject or noise reject minimizes the effect of noise and may reduce jitter in the display caused by noise. Try toggling. I don't think AC will do anything very interesting. High frequency reject, low frequency low frequency reject. That's interesting. I wonder, what is it doing? Noise reject. So just pushing these buttons doesn't tell me anything because I don't know what it is doing. Since the function generator signal is quite clean, you may not see much of a difference in the display for these 3 coupling modes. Some of the circuits you'll build in this course have significant noise, in which case high frequency reject or noise reject may be helpful. Okay. Selecting mode, displays auto, normal, and hold off. Auto trigger is useful for displaying a signal with unknown voltage levels. Right, so then you can see where the signal is before you set the trigger level. Normal forces the scope to wait for a trigger. Normally you want to be in normal mode. Switch to normal mode. Here we go, switch to normal mode. Increase the trigger level until it is bigger than the waveform. Okay, so here's the trigger level. So I'll turn it up until it's bigger than the waveform. and now it will stop triggering. You see, so now there's trigger question mark. See, it still says run, it's waiting for a trigger, but it says trigger question mark, so it doesn't update. So then, for example, I can turn off the output here, and you see the scope still displays the last trigger because it's waiting for a trigger. And I can move the trigger level back down, and it, oh, okay, I guess, oh, I see, once I cross 0 it updated because the signal coming in is 0. Okay, so I can turn this back on, it's triggered. But we're in normal mode. I can turn this off, and now the signal stops arriving. So now it's waiting for a trigger. So you see it says trigger question mark. It's just waiting. So it still says trigger question mark, and then I can turn the signal back on, and it says triggered. Hold off is the minimum time between one trigger and the next. And normally you want this to say set to minimum. I think that can be powerful if there's a burst of activity now and then, and you want to catch the beginning of that burst of activity. Turn the trigger level to something close to 0 volts. Okay, here we go. Something close to 0 volts. Now we will investigate the effect of scope input coupling on the trigger level setting. Set channel 1 on the function generator to output a 500 millivolt peak-to-peak sine wave. So amplitude 500 millivolts peak-to-peak, offset by a DC level of 4 volts. Okay, so offset 4 volts DC. You see we're waiting for a trigger. So before we added the offset we were triggering, and now we're waiting for a trigger. Increase the trigger level. By the way, every time I increase the trigger level, this thing says pre-trigger, meaning it's loading up its memory buffer with samples. It's way up there. I guess I have to change the scale. Let me change the scale to 2 volts per division. There. Now it says, okay, now it says triggered. It is interesting that sometimes the trigger level displayed by the yellow horizontal line doesn't quite match what you see on the screen. I don't have a good explanation for that. At around a trigger level somewhat above 4 volts, you should see the scope begin to trigger. Triggered should be displayed. Trigger sensitivity depends on the AC signal displayed, and if the AC signal on top of the DC signal is small, the trigger sensitivity is not very good. Now change the channel 1 input coupling to AC, not the trigger coupling, the channel 1 input coupling. Okay, here's channel 1. We'll do push channel 1, we get the channel 1 menu, and we'll say coupling, and we'll go to AC coupling. Okay, I'm going to do a different order from the instructions. I'm going to go down with the trigger level until we start to trigger again. Okay, so there we're starting to trigger, and then I will increase the scale. So this is 2 volts per division, 1 volt per division, half a volt per division, 0.2 volts per division, 0.1 volts per division. So there it's waiting for a trigger. Now it's triggered. Notice that, as expected, the DC offset has been removed from the signal. Return channel 1 on the function generator to the previous default sine wave. Okay, let's do that. So we'll say 0 offset. So here we go. 0 volts DC offset, amplitude 5 volts peak to peak, frequency 1 kilohertz. Okay, so now you see a bunch of vertical lines because the signal is so much larger. So you see this is 1, 2, 3, 400 millivolts, but the amplitude is 5 volts. So you can see when you're zoomed in like that, the sine wave, the part of the sine wave that you can see looks like a bunch of almost vertical lines. Set the scope channel 1 input coupling to DC coupling. Adjust the trigger level to about 0 volts. Okay. The slope menu option. Now, by the way, I think this is hard for you to understand the way it looks right now. So I'm going to change the scale, 200 millivolts, 500 millivolts, 1 volt per division. Now you can see the whole sine wave. Okay, so the slope menu, so we'll go back to trigger menu. So that's positive slope. In fact, here, let me zoom in on the time axis. So now we have 200 microseconds per division. So you can see that where the scope triggers is where the waveform goes from negative to positive. So if I change the slope to downgoing, now where the scope triggers is where the waveform goes from positive to negative. So you can tell it, I want you to trigger when I go from above to below threshold, or you can tell it, I want you to trigger when I go from below to above threshold. Now if we push run stop, and the triggered goes away, and it says stop up here. You should see that the trace freezes. You will see stop displayed in the uppermost left-hand corner. Now increase the trigger level to about 1 volt. Okay, so there is about 1 volt. If we press single, we're going to get one trigger, and it's going to trigger when this part of the waveform, going from a little below 1 volt to a little above 1 volt, is at this point beneath this trigger icon. So I think we're going to see what looks like this sine wave shifted over to the left such that the waveform crosses positive 1 volt in the middle of the screen. Let's see. I'll press single. Ha! As predicted. Do you understand the change? Oh, that's a this is a rising edge. So let me do, now I'll make it a falling edge. So now what we should see is this part of the waveform should appear in the middle of the screen, because this is where it goes from just above to just below 1 volt. So let's push single again. Yeah, okay, cool. And then I'll go back to rising edge, push single again, and I'll go back to 0 volt trigger level and push single again. And then I guess I'll just push run. So the stop button is useful if you see something and you want to freeze the screen display and not have it overwrite what you're seeing, because maybe you want to preserve the display while you change the circuit, or maybe you see something that only occurs once in a while and you want to stop it so it doesn't go away. So stop prevents the scope from continuing the trigger. And then sometimes you want to stop it from automatically triggering, and you just say, okay, I want you to trigger once. So then you just get one waveform exactly when you ask for it. And that can be useful too, especially if you're looking at something intermittent. Though in this course you will seldom look at things that are intermittent. Okay, you should keep reading the text here. The scope can report quantities of information about the traces displayed. I usually like to use the cursor, so you can turn on the cursors, and then I think you can select vertical cursors or horizontal cursors. So if you want to know how big vertically is this waveform, I like to do it with the cursors. And then if you can ask what is the period of this waveform, I like to do that also with the cursors. The half period is about 500 microseconds. That makes sense because the full period should be 1 millisecond. Okay, that's right. So we're going from minus 500 to plus 500 microseconds. That's a difference of, well, it says 998.0 microseconds. So believe it or not, this says cursor A is at plus 498 microseconds, cursor B is at minus 500 microseconds, and the difference between the two is 998 microseconds. So that's horizontally. And then I guess we can do select. I'm trying to figure out how to get it to tell me the numbers vertically. See, so I think the trigger menu was in the way of the vertical display. So it says A is at a vertical position of 2.460 volts, B is at a vertical position of minus 2.520 volts, and the difference between them is delta is 4.980 volts. So that makes sense. 5 volts peak to peak, and 1 millisecond, which is 1,000 microsecond period. So that's with the cursors. So if you do push and hold cursors from menu. Okay, this is source. Oh, cursors waveform screen. Source selected waveform. Okay. Bottom leftmost tab. Verify for cursors you've selected screen. We did that. And second leftmost tab, for source you've selected channel 1 of the scope. Well, this says selected waveform, but I guess we could say channel 1. Use the bars tab to select horizontal. I see. Right, and go back and forth between horizontal and vertical. I think you can also do that by using the select button. Okay, now press the measure button. We can push the measure button. Okay, I push the measure button. Press the lower left-hand tab to add measurement. Okay, add measurement. So this says add measurement. Select the same channel. So source is channel 1, measurement type. So we could select amplitude. We have to turn knob B. Okay, so we can say amplitude. Okay, add measurement. And then we can go up with knob B. I guess we could say frequency, add measurement. Then I can do menu off. And you see, it says amplitude 4.96 volts, frequency 1.000 kilohertz. And then mean, minimum, max, standard deviation. So the measure feature is often pretty useful, though I personally prefer to use the cursor. This is an absolutely true statement. The function generator and scope have many more features yet for you to discover. So I think you should feel free to experiment with them. And there are some fancy features of the function generator we'll use later in the course. In real life, we want to use the oscilloscope with scope probes, which look like this on the end. It plugs into the oscilloscope, and like this on the other end. And most likely for your scope, there will be 4 scope probes, each one color-coded, so that the yellow, blue, magenta, and green colors match the yellow for channel 1, cyan for channel 2, magenta for channel 3, and green for channel 4. It may not necessarily be true that every scope has those 4 colors nicely arranged, but when the colors match up, it does make it easy for you to see which scope probe you're picking up without having to trace through the wires. Okay, so we want to connect a scope probe to channel 1 of the scope. So I have to unplug this coax cable, and I'll plug in the yellow striped scope probe to channel 1. And then I'll take the head of the probe and I will clip it to, now this is a little bit confusing. On the bottom right corner of the scope, the upper connection says ground and the lower connection says probe compensation 2.5 volt square wave. So my intuition would think that the ground is down below and the signal voltage is up above, but it is in fact the opposite way. The ground is up above and the voltage is down below. So I want to take the head of the probe and I'll connect the ground clip to the ground, and I'll connect the, so you notice that there's a little spring clip here. So if I pull this little spring mechanism back, then it reveals the little spring clip, which then I can clip onto a nearby hook. Okay, so I have the head of the scope plugged into this probe compensation electrode, and I have the ground clip of the scope plugged into this ground electrode. Select channel 1 on the scope. Set the scope to trigger off the channel 1 signal by pressing the menu button. Okay, trigger menu, source channel 1. That seems all fine. Adjust the level knob. Oh, I see. So we're set at 10 volts per division. So the scale changed by a factor of 10. The scope is smart enough to know when a scope probe is plugged into it. And for reasons you'll understand later, the scope probe actually reduces the amplitude of the signal presented to the scope by a factor of 10. But the scope knows that, so it changes the display scale by a factor of 10. So what had been 1 volt per division becomes 10 volts per division, because it would take a 10 volt signal at the tip of the probe to produce the same 1 volt signal internally inside the scope, it turns out. Adjust the trigger level to around 1 volt. Okay, trigger level is around 1 volt. Also, I think I can go to the measure menu here, and I can say remove measurement, remove all measurement, and then push menu off. Menu off is often a useful button for decluttering the screen. Okay, I think I can also turn the cursors off. Set the channel 1 vertical scale to 500 millivolts per division. Then set the horizontal scale to 200 microseconds per division. Okay, it's already that way. Move the trace down. This is a useful thing to know. So when you move this knob counterclockwise, you see it moves the 0 volts position lower on the display. So we can move this maybe so that it's roughly centered. And then I think I can change the horizontal position so that the trigger happens right in the middle of the screen. Okay, then we have this picture. So this is what a properly compensated scope probe produces, and it seems as if our probe is pretty close to compensated. The middle picture shows what happens if you have too much high frequency content in your square wave, and the right picture shows what happens if you have too little high frequency content in your square wave. So you know a square wave is a sine wave with frequency f plus 1/3 of a sine wave with frequency 3f plus 1/5 of a sine wave with frequency 5f plus 1/7 of a sine wave with frequency 7f, and so on. So if you have too much of the high frequencies, you get an overshoot. And if you have not enough of the high frequencies, then you get a rounded corner. So there is a little hole in the side of the scope end of the probe that says probe comp. And there's a little screw inside there. And there is in your, one of the drawers next to your desk says scope parts, including probe tuning tool. And I think one of these two, there's a tiny little screwdriver that looks like this, and there's a longer screwdriver that looks like this. One of these will do it. Let's see. Let me try the longer one. Yeah, I guess that works. Okay. So you see, now we have not enough high frequency content, and this is just about right. And now we have too much high frequency content. So you want to turn this until your square wave looks nicely square. You should not have to do this very often, but it is worth checking. So this is a pretty good suggestion anytime you're about to use a scope probe, especially if you weren't just recently using that same scope probe. You probably want to connect it here to check that it is compensated. I think you don't want to be in the habit of turning the screwdriver back and forth every day, but simply plugging it in to make sure a square wave looks nice and square is not a bad idea. So I will now do that with the other 3 channels of scope probe, so that I have an oscilloscope set up with 4 scope probes plugged in. Here is the blue channel 2. Turn channel 2 on, and I'll move the channel 1 scope probe compensation device. And then I can plug in, here's channel 2, and here's channel 2's ground lead. Change the voltage setting to 1 volt per division. And I'll change my trigger source to channel 2. Okay, menu off. That looks good. That looks like a nice square wave. I can remove that. And then I'll pick up the magenta scope probe for channel 3, and I'll plug it in. Before I started doing the scope tutorial, all 4 of these probes were plugged in. Okay, I'll plug in the ground clip and spring clip channel 3. We'll turn channel 3 on. It is at 1 volt per division. I'll do oh, by the way, notice that nothing is triggering. So if I change the trigger mode to auto, see if I push this right hand button, I go to auto, this is actually quite informative right now. I see that there is a waveform on channel 3, but it is out of sync with the trigger because I'm still triggering on channel 2. So then I can go over to trigger menu and do source, and I can use the A multi-purpose knob to get channel 3, and now I have a nice stable, I can do menu off, I have a nice stable square wave. That looks like a nice square wave, so I don't need to adjust anything. And then I'll find the green scope probe for channel 4. I will plug it into channel 4, and then I'll plug that into the ground clip scope compensation contraption, turn on channel 4. Okay, there it is up there, and then I can do trigger menu, trigger source, channel 4, menu off, and I can move channel 4 down. I think actually if I push this in, no, it doesn't work. Some scopes, if you push it in, it goes to 0. Then I'll change the scale, so I have a nice visible sine wave. This looks fine. Okay, so there was no need to do any scope probe compensation, but we did check the compensation. So that ends the tutorial part of the scope function generator tutorial. Finally, we'll move on and actually use the scope for something. Part 4. Using 2 resistors, draw the schematic for, and then build a voltage divider that will take a 1 kHz sine wave at 10 volts peak to peak, and produce a 5 volt peak to peak sine wave as output. So I guess we want 2 equal resistors for that. The output should have 1/2 the amplitude of the input. We actually have specific resistor values in mind. Your voltage divider should have a Thevenin resistance of 1 kilo-ohm. So in that case, we want to use a pair of 2 kilo-ohm resistors. So here is our signal source, and we'll have one resistor which is 2 kilo-ohms, and then here is our output, and then we have another resistor which is 2 kilo-ohms, and this point on the circuit we will call ground. So I think this is what we want to build. Now, by the way, the output resistance of the function generator is 50 ohms, and the series resistance of these 2 resistors is 4 kilo-ohms. So there will be a roughly 1% effect on the output of the function generator due to the finite resistance of these resistors. But 1% is right at the edge of our ability to see with the oscilloscope, so we probably won't notice it in this case. Okay, so now I guess we want to build this. So we will use channel 1 of the function generator. Okay, and this is channel 1. Now there actually are a variety of ways you can get the signal from the function generator onto the breadboard. One way that I used to be quite fond of is to use, so the bottom left and bottom right corners of the breadboard have little BNC connectors, so you can run a coaxial cable from the function generator output over to this BNC connector, and then you can run a little piece of wire over to wherever you want to use that on your breadboard. I find that convenient, but for now I'll follow the directions seen in the lab. So if we go over here to this bin, then one connector available in the bin, actually there are 2 copies of it, we have some cables that have a BNC coaxial connector on one end, and it is a piece of coaxial cable, and then the other end is a pair of spring clips. So that's what we'll use in this case. So I'll plug this into the channel 1 output of the function generator, and then I'll wire this up to the breadboard. Now I need wires, or I guess I could clip them onto resistors, but I need some way to go from these spring clips to the breadboard. So I will use the same red and black wires that I had been using for the power supply. I'll run the black wire from the function generator spring clip to the ground row down here, and I'll put the red wire in some randomly chosen node of the breadboard. I don't want to put it up here because it's really a signal voltage. It's not really a power supply voltage. So I won't put it up here, which would be sort of treating it as if it were a power supply voltage. Then we happen to have a drawer labeled 2 kilo ohms right at our workstation. So I'll take out a pair of 2 kilo ohm resistors, and I expect these resistors to read red, black, black, brown. So I guess I can check that. That seems promising, but I think I'll measure them to be sure. So I'll take Mr. Ohm meter on ohms mode with the red wire plugged into the volt ohm input. And let's see if we get approximately 2K ohms for each one. 1.9973K, 2.0003K. Alright, so I'll go from this signal source over to some node like that, and then I'll go from that same node down to ground like that. So this is where the signal source goes. This is the output node, so it corresponds to this point on the schematic diagram, and then this goes down to ground. Connect the oscilloscope to observe V in versus time on channel 1 and V out versus time on channel 2. Okay, well, first, let me show you what I'm going to do with the function generator. Here we are, sine wave, and we want to, so the frequency is 1 kilohertz. Let's change the amplitude to 10 volts peak to peak. Offset should be 0. I think that's good. And the output is enabled. Okay, so then we will go channel 4 we can disable, channel 3 we can disable. So we'll make channel 1 show V in versus time. So I'll pick up the yellow scope probe, and it is nice to ground the ground leads. I'm just going to clip this ground lead onto the grounded end of this lower resistor. That's kind of a convenient place to put it. And I'm going to clip this end of the scope probe onto the left-hand side of this resistor. I could use a little piece of wire for that. It is kind of nice sometimes to use a little piece of wire, because then you can move around from place to place on the breadboard without finding something new to clip onto. But for the moment, I'll just clip onto the left side of this resistor. Now, the scope display looks as if it's gone crazy, but I think there are a couple of issues. One is that the voltage scale is not commensurate with the signal we're looking at. Okay, so there we go. Now we see the span of the waveform, and I can push the vertical offset knob. I can turn the vertical offset knob to center that waveform, and I can change the scale to, I guess 2 volts per division is nice, so then I see the whole waveform. And you say, why does it look like a big blur instead of looking like a nice sharp waveform? It's because I'm still triggering on channel 4. So I want to change my trigger source to channel 1. Now I see a nice steady waveform. Then let's take the blue scope probe for channel 2, and I can connect its little ground clip to this same grounded end of the lower resistor, and then I'll connect its main clip to the right-hand side of the first resistor. Now you say, gee, this is weird, the 2 sine waves appear to be the same size, but notice that channel 2 is on 1 volt per division and channel 1 is on 2 volts per division. So that is a nice way to see that they have a nice 2-to-1 ratio. You can click 2, you can click 1, and they really are nicely on top of one another. But if we change the scale for channel 2, 2 volts per division, now they're on the same scale, and you can see that the channel 2 signal is half the size of the channel 1 signal. So that makes sense. The voltage divider equation works time point by time point. So the voltage divider does indeed behave as I expect for a time varying input. At any given instant, the input is amplitude times sine of 2 pi ft, and the output is just 1/2 of that. Okay, so this was a pretty straightforward initial use of the scope, and I guess we can draw the waveforms. So we'll say here's time, and here's the voltage as a function of time, and here's V in, and here's V out, and this is 5 volts, this is minus 5 volts, this is 2.5 volts, this is minus 2.5 volts. Okay, so I think that's it for part 4 of Lab 3. That didn't take too long. This is our first actual use of the oscilloscope, so that's kind of exciting. I think this is a good place to wrap up, because now when you come into class on Tuesday for your first chance to work with the real hardware instead of just seeing me work with it, you will repeat the scope tutorial, and then we're going to start with this very same voltage divider, which is just a purely resistive voltage divider, and then you're going to generalize it to a voltage divider that combines resistors and capacitors, which will lead into the idea of frequency-dependent filters. And this device, the oscilloscope, really will be your eyes for a good chunk of the rest of the semester. It's how you see what's going on inside a circuit that you build.